Okay, thanks for joining me today. Today, we're going to be talking about differentiable functions and continuity. And in particular, we're going to be looking at and proving a theorem that says if a function is differentiable at some point, then it's also continuous at that point. So in order for us to do this, we first need to recall what is the definition of differentiability. So recall that the definition of differentiability is that if a real valued function, so we're only dealing with numbers that are real valued. So that means we're just talking about real number system right here. So if a real valued function is differentiable at some point A or some value A, then f prime of A exists. So this is the definition. If the derivative exists, then the function is differentiable. And that's considered to be differentiable at a point. But it could also be differentiable on what we call an open interval from A to B. And here we're saying it's not necessary that A or B are finite. So it means A could be negative infinity, or I could have negative infinity to positive infinity, or I could even have like this, okay? Or it could be two finite numbers, doesn't matter. But we say that the function f is differentiable on this open interval if it's differentiable at every number in that interval. So also notice it doesn't require it to be differentiable at the endpoints. Okay, so let me clear that. So the definition of differentiability comes down to saying if the function is differentiable, or I'm sorry, I said that wrong. The definition of differentiability comes down to saying that the function is differentiable if f prime of A exists. So you might say, well, that doesn't make sense. But what is f prime of A? So if you remember from the limit definition of the derivative, f prime of A is in fact this limit that we define in this manner. So the limit as h goes to 0 of f of A plus h minus f of A over h. So this, remember, is the slope of the line tangent to our graph f at the point A. Right? And we can calculate that slope of that tangent line, which coincides with our function. And therefore, this is going to be the instantaneous rate of change of our function. Hold on a second. Okay, so then the derivative, in other words, this will give us the value of the derivative at A. All right, so here, what I want to do is just change my notation a little bit. So recall that h is actually the distance between some A and an arbitrary x that's not necessarily equal to A. So I could set h equal to x minus A. And then I'm just going to go through this formula and replace the h with x minus A, because this formulation that I have here is going to be much more useful. All right, so what I'm going to do, like I said, I'm going to replace the h with x minus A throughout the formula until I get this expression here, which is exactly the same, but with different notation. Here I have x minus A going to 0, and I just change that into x going to A. Same thing, right? Okay, so then now let's go back and look at then what's the definition of continuity. So if you recall, a function is said to be continuous at number A. And again, we're only dealing with real valued functions if the limit as x goes to A for f of x is equal to the value of f at A. Okay, so implicit in this definition is that, number one, the limit exists, which means that the left side limit and the right side limit exist. And then also the function is defined at A. Okay. So furthermore, f is continuous on the interval if it's continuous at every A in the interval. So again, we start by defining, just like differentiability, we define it at a point first, and then we expand that to say if it's differentiable or if it's continuous on an interval, then it's going to be, it will have this condition at every value in the interval. I don't want to say point because point implies two-dimensional. So when I say value, I mean like every, well, it could be every point. So every x value, we meet this qualification, and the same thing for differentiability. Okay, so then our theorem is that a real valued function f being differentiable at A implies that f is continuous at A. So if the function is differentiable at this point, then we know that it is definitely continuous at that point. Okay, so this is what we're going to prove today. And the idea of the proof is like this. We're going to look at this definition of differentiability that I reformulated on the previous slide. And then we're going to look at, can we take that expression and rewrite it in such a way that it is the definition of continuity? So do we get that? Can we end up with an expression that says the limit as x goes to a for f of x is equal to f of a by starting with this definition of the derivative at a? Okay, so that's our idea of the proof. So let's go ahead and go to the proof. So I'm going to do now is change my screen share, and I'm going to duck out of the recording now, turn off the video. All right. So let's get started here with the proof. And let's see, can I make this a little bit bigger? There we go. So we're going to prove if a real valued function f is differentiable at a, then f is continuous at a. So I'll start just by writing proof. Okay, so then I'm going to write let f be a real valued function differentiable at a. Okay, so that's just like our very first preliminary statement. So let f be real valued function that is in fact differentiable at a. So what does that mean? That means that f prime of a exists. Okay, so then f prime of a exists. And we know what that is. We know that f prime of a is equal to the limit as x goes to a for f of x minus f of a divided by x minus a. Okay, so here's our expression for the derivative. So we know that this derivative exists. All right, so, and we know that this function, so we know this function is differentiable, which means we know this derivative exists. I took a sip of coffee here. So our idea is we're going to use this expression and try to come up with this idea of this definition of continuity. So what I want to do is take a look at this quotient. Okay, so let's say, let me put a period here. So look at the quotient. So our quotient is f of x minus f of a divided by x minus a. And we're going to make the qualification here that x is not a, which in fact it won't be. It could get infinitely close to a, but never actually be a. So we're going to look at this quotient, and then we're going to rewrite the expression. So we can write on the left-hand side, I'm going to write f of x minus f of a. And then on the right-hand side, I'm going to write f of x minus f of a divided by x minus a, and then I'm going to multiply to that x minus a. Okay, and so these two expressions are equal, provided that x is not equal to a. Okay, so we make that qualification here. Okay, so now I've got this expression, and this is basically the direction I want to head into, because now what I'm going to do is attempt to come up with that definition of continuity. And you can see on the left-hand side, well, of course, I've already done this proof, so I know what I'm supposed to do. But this type of proof, the way that we do it is we know how we need to end up. And so we sort of make our steps in such a way that we do end up in that place. So let me show you what I mean. So we took this expression, we took this quotient, and then we reformulated it again. I multiplied by x minus a to both sides. And now what I'm going to do is go ahead and take the limit as x goes to a for both sides. So on the left side, I'm going to get f of x minus f of a. And on the right side, I've got the limit of a product as x goes to a. So I'll have f of x minus f of a divided by x minus a, then multiply to that x minus a. Okay, now we can work on the right-hand side for a moment and recall that the limit of the product is the product of the limits. So I can essentially, it's similar to distributing. I can apply this limit to both of these expressions individually, like so. And now I need to say something about how I can evaluate these two limits. So the first thing you can notice here is that this expression is precisely f prime of a. And we know f prime of a exists because that was one of our assumptions. So I know that I've got f prime of a here. And this expression here, now we said x is not equal to a, but we do have a monomial, not a monomial. We do have a monomial, but we do have a linear function here, which means it's a polynomial, and a polynomial is continuous everywhere, which means that we can use the direct substitution property and we can substitute a for x. And that means that for this limit, we will evaluate to 0. So we're going to get 0 here. All right, so that means that now we've got this expression. We have that the limit as x goes to a of f of x minus f of a. This is equal to 0. Okay, now we're very close to what we want to show, because what we want to show, so then consider this limit as x goes to a for f of x. We want to show that this is equal to f of a. Okay, that's our goal, but instead what we're going to do is apply a limit here, and I'm going to put this in a bracket, and I'm going to add to it f of x minus f of a, like this. So essentially, this is sort of like adding 0 in a sense. I added, wait, did I do this right? Hold on a second. Something is, oh no, it's, no, hold on a second. Something is awry. X minus a. No, it's fine. Okay. So then now I've got two equal expressions. Why? Because both sides, I basically just have the limit as x goes to a is equal to f of x. Okay. And why don't I just prove it to you? Okay. Because you probably can figure it out if you don't know it already, but let me just write this down and I'll expand it. So I've got this, and but I added to that. So here's what I did. I had an f of a over here. Actually, hold on a second. I think I need to write down the limit closer to the equal sign so I have enough room. Okay, so here's what I've got. Let me just write it like this. So these two things are equal, you'll agree. And then all I've done is add and subtract the same thing. But I have rewritten it like this. And the reason I have rewritten it like this is because we happen to know what one of these limits evaluate to. Okay, so in particular, we know that, let me reformulate it again. So I'm going to write f of a plus, and then parentheses f of x minus f of a. And then close the bracket, and that should be a minus sign right here. So let me go and fix that. Okay, So now what we're going to do is we're going to recall that we can split up the limit by the sums. So the sum of the limit is the limit of the sums. So I'm going to get the limit as x goes to a of f of a plus I'm going to apply this limit here. Also, and the reason is because we know what this limit is. Here, we know that this one will evaluate to 0. So this is 0, we already know because we proved it earlier. And so now we have this expression. So we have the limit as, what am I talking about h for? As x goes to a for f of x, this is equal to the limit as x goes to a for f of a. Now, what is f of a? F of a is a constant value. And if you take the limit as x is moving for some constant value, well, what exactly happens there? It's like you have a constant value is just a horizontal line. And so if we change our x values, it doesn't really matter because we still have the same value no matter what happens with x. So that means that here, the limit as x goes to a for f of a is simply, again, f of a. And now this is precisely our definition of continuity. So we have shown that if f has a derivative at the point A, then it also will be continuous at the point A. Okay, so let me make that nicer. So that concludes the proof. And so what we can say now with 100% certainty is that if f is differentiable, I'm going to abbreviate, then f is continuous. And I'm also leaving off the at a part, but that is also correct. So big mistake that people make. So note that the converse of this is not true. So if f is continuous, then f is differentiable is not true. And this is just a very common logical error. So to prove to you that it's not true, I have an example. So let me go back to my presentation. And we'll take a look at the reasoning behind this. So the example I'm going to use is with the absolute value function. Okay, so the absolute value function f of x equals the absolute value of x is continuous at 0, but it is not differentiable at 0. So f prime of 0 for this function does not exist. The function does have a derivative, but it's a piecewise function. Well, of course, absolute value of x is also a piecewise function. So let me, while I'm here, let me just write down the definition of this so everybody can remember. So remember, this is, it's x if x is greater than or equal to 0, and negative x if x is less than 0, like that. Okay, so that's our definition of the absolute value. Okay, so so we're going to first prove that it's continuous at 0, and then we'll show that the derivative doesn't exist at 0. All right, so let's take a look. Okay. So we can see that the function is continuous at 0 because, first of all, if you plug in 0 into the function, you get 0 back out. So the function is defined at 0, f of 0 equals 0. So in order for the function to be continuous at 0, the limit must also be equal to f of 0. And if we take the limit, we get that the limit on the left side of 0 is going to give us 0, and the limit on the right side of 0 will also just give us 0. So we can essentially use the direct substitution property here. And we get 0 in both cases, which means that the limit as x approaches 0 for this function is equal to the value of the function at 0. So that means that, in fact, it is continuous at 0. So now we need to show that it's not differentiable at 0. So in other words, that this limit cannot exist at 0. And so the way we do it is we're going to look at the limit of this expression on the left and right side of 0. Okay, so first of all, we look at the left side limit and recall the definition of the absolute value function. If we go from the left side of 0, then our absolute value of x can pop out as a negative x. And of course, plugging in 0 here, we get 0 and 0. So we get negative x minus, negative x divided by x gives me negative 1. Okay, so that's the left side limit. And so what that's saying is that, well, I'll show you in the graph here in a moment. Okay, so the next one we want to go to, we're going to look at the right side limit. So on the right side, of course, x is positive. On the right side of 0 or at 0, x is positive. So when I plug in the 0, same thing happens. I get over here, these are 0, and then on the right side of 0, absolute value of x is positive. So I get x divided by x, which is 1. And so here we have a problem because the left side limit is not equal to the right side limit. And what that means, as far as limits go, is that this limit does not exist. So there is no value for the derivative of this function at 0. So we're going to say f of x, f prime of 0 does not exist for the absolute value function. So that means that we have seen now an example of a function that's continuous at a point, but at that same point, it's not differentiable. So continuity does not imply differentiability, but differentiability does in fact imply continuity. Okay, so here I just have the geometric interpretation. I've got the graph of the absolute value function in blue, and then I have the derivative of the absolute value function. So the absolute value function is in blue, and the why don't I write that in blue? That doesn't matter. And the derivative, which is actually this expression here, this is very strange. The pen is being a little bit weird when I use it on Zoom. Okay, so that's the derivative of this function, and you can see immediately that when you look at the derivative as a function, you can see it's not defined for 0, right? But outside of that, let's take a look at the geometry of the situation. So here's my absolute value function, and you can see that it's a linear function on the right side of 0 and at 0. And so the derivative of that function would be the slope of this line. The slope of this line happens to be 1. And so it's not surprised that our derivative is a constant value equal to 1. Right? And that's because that derivative function, which is just a horizontal line, does in fact tell us the derivative at every point for this absolute value function on the right-hand side of 0. On the left-hand side of 0, and not including 0, we have a decreasing linear function, which is basically, the same line reflected over the y-axis here. So this slope is -1, and therefore it makes sense that the tangent line is a horizontal line that is -1. And so then the problem here for differentiability is that we've got two different tangent lines at a point here. And so we cannot have a limit because the limits don't agree, right? Okay, so that concludes this presentation. So remember, if the function is differentiable, it's continuous, but if it's continuous, it's not necessarily differentiable. Now, you will use this in a couple of theorems. Definitely continuity is one of the key requirements for many of the theorems in calculus, because continuity allows us to take advantage of that property of the real numbers, wherein the real numbers are a complete ordered field, which is a very nice thing. And we're not going to talk about that in this video, but perhaps in a video to come. So thanks for watching. Hopefully this was helpful.